Dear students, today's topic of my lecture, Electromagnetic Induction, Part 3. Two parts I have already explained and the videos are uploaded on my YouTube channel. You can subscribe it. Now, what we have to learn in this Part 3 and that you see here, I will explain self-induction and self-inductance and then self-inductance of a long solenoid. After that, magnetic potential energy in an inductor. Then recapitulation in the form of multiple choice questions. So one by one I explain. So first, self-induction. So what is basically self-induction? And the self-induction is the process or the phenomena when a current in a coil increases or decreases. Then there is a change in magnetic flux linked with the coil. Hence, an EMF is induced in the coil. This is called self-induced EMF and the process is called self-induction. Now, how you can understand this process? So that process we can understand with the help of Lenz's law. So according to Lenz's law, the direction of this induced EMF is such that it opposes the cause that produced it. Now, what is the cause of production of induced EMF? That is the change in magnetic flux through the coil. And how the change in magnetic flux through the coil takes place? That takes place when the change in current through the coil. Hence, induced EMF will oppose change of current in the coil. If current in the coil is increasing, the induced EMF will oppose the increase in current. On the other hand, if current in the coil is decreasing, the induced EMF will oppose the decrease in current. And that you can understand by these diagrams. So you see that here in the diagram, there is a coil which is connected to a key and a cell. And here in the first diagram, we are increasing the current by closing the key, and the same diagram is here by opening the key, then the current decreases. So one by one, you understand it here. In the first diagram, if we close the key, then what happens? Then the current starts increasing from 0 to maximum through the coil. So when the current increases through the coil, then increase in magnetic flux linked with the coil and an EMF is induced. This induced EMF will oppose increase in current and its direction is in the opposite direction of the current. Similarly, what happens if we release the key? Now the key is open. Then the current in the circuit or through the coil, it starts decreasing. So decrease in current, again decrease the change in magnetic flux through the coil. So if decrease in magnetic flux through the coil, then an EMF is induced. And this induced EMF opposes the decrease in current. Therefore, its direction is in the direction of decrease in current. And that process is known as self-induction. And that we can understand by an experiment you can see here. So here we have taken one coil and one resistor, battery, two bulb B1 and B2, and this is the tapping key. This coil is known as inductor. So what happens when we make the connections? The bulb B1 that we connect to this resistor, and the bulb B2 that we connect to the coil, right? And then we see that what happens and the how the bulb B1 and B2 behave, so that we can understand the phenomena of self-induction. Behave means which bulb will get glow earlier when we close the circuit or close the key, and which bulb will take longer time to glow up. So let us see here. Self-induction or self-inductance is the property of a coil by virtue of which the coil opposes the change in the current, whether growth or decay. Now you see that here we make the connections, and this B1 is connected to the resistor of resistance R, and B2 is connected to the inductance of L, and the connections are made to the battery also along with the key. So when we press the key, then what happens? You see that the bulb B1 glow immediately, but B2 will take a longer time. So why this so happens? This is because as the current passes through the coil, then what happens? An EMF is induced, and this induced EMF will opposes the change in the strength of the current, due to which the bulb B2 will takes longer time to glow up, whereas B1 is connected to the resistor of resistance R. Here there is no induced EMF, that's why the bulb B1 glow up immediately. But if we release the key, then what happens? B1 immediately gets stop glowing, but B2 will take some time. This is because of induced current is set up in the direction of the current developed by the battery. So this is known as the experiment of self-induction. So what we observe from this experiment, very clearly we observe when the bulb B1 is connected to the resistor of resistance R, and in that condition the bulb B1 glow up immediately as we press the key. But bulb B2 will take longer time because it is connected to a coil or the inductor, and in it a induced current is developed, and that induced current opposes the change in the strength of the current, which is increasing through the coil. So that's why the bulb B2 will take longer time to glow up. Similarly, when the key is released, then the current starts decreasing. But what we observe that the bulb B1 immediately stop glowing, but B2 will take longer time to stop. That is because of the induced current which is developed in the coil and is in the direction of the current produced by the battery. So here we can say that when the bulb is connected to the resistor of resistance R, then it glow up immediately because there is no induced current in it. But whereas a bulb which is connected to a coil of inductance L, then it takes longer time to glow up or stop glowing because of induced current, which is in the direction of current produced by the battery. Now, self-inductance. Self-inductance, basically it is the property of the coil by virtue of which it opposes any change in the amount of the current flowing through it by inducing an EMF itself is called its self-inductance. Just I explained in the experiment, and that you can also understand practically when a tube light when you switch on, then it takes longer time to glow up because in it there is a choke coil and that consists of inductor, whereas a bulb glow immediately. So that is because of the self-induction phenomena. In the choke coil, there is a inductor, and when tube light is switched on, then in that inductor an induced EMF is produced and induced current is developed, which opposes the growth of the current. So that's why it takes longer time to glow up in comparison to the bulb. So now we have to find out the coefficient of self-inductance. Now we say that let I is the current flowing through a coil at an instant, then it is found that magnetic flux in the coil at that instant is directly proportional to the current passing through it, and hence it is expressed as, obviously, when the current is increases, then more increase in magnetic flux linked with the coil. So that's why the magnetic flux linked with the coil is directly proportional to the current passes through it. And therefore, we can say that phi directly proportional to I. For omitting this proportionality sign, we require a constant, and that constant is L. So this L is called constant of proportionality and known as self-inductance or coefficient of self-induction. Now, if we say that I equal to 1, then by this expression L equal to 5. So we can define numerically the coefficient of self-inductance is numerically equal to magnetic flux linked with a coil when unit current passes through it. Similarly, we also know that the induced EMF in the coil is given by E equal to minus N d phi B upon dt, and that can be expressed like that minus L di upon dt, because phi b equal to Li and L is constant, so you can write minus L di upon dt. Now if we say that N equal to 1, N is the number of turns of the coil. So in that condition, what you are getting? E equal to minus L di upon dt. Now we say that if di upon dt means the rate of change of current is unity, then in that condition, by this expression, what you will get? L equal to induced EMF. The same way we can also define as the coefficient of self-inductance is numerically equal to induced EMF in a coil when the rate of change of current is unity. So this is about the coefficient of self-inductance. Now the units of self-inductance, on the honor of the name of scientist, its unit is Henry. But by the formula phi equal to Li, then L equal to phi upon I, and phi is the magnetic flux which is measured in Weber and the current is measured in ampere. So that's why another unit is Weber per ampere. Similarly, by the another formula E equal to minus L di upon dt, when we find the unit of L, it comes volt second per ampere. Now we have to find out an expression for coefficient of self-inductance of a long solenoid. So for that purpose, we take a long solenoid of length L, area of cross section capital A, carrying the current I, and then if solenoid is carrying the current I, then a magnetic field developed inside the solenoid, and that magnetic field is equal to B equal to mu naught Ni, and magnetic flux linked with the solenoid, that must be equal to magnetic flux linked with each turn of the solenoid and then the number of turns of the solenoid. So that's why we can write mathematically like that: phi equal to BAN equal to PAN. Then you substitute the value of B from here and it comes to be mu naught NIAN, where N is the number of turns of the coil, B is the magnetic field inside the solenoid because of the current flowing through the solenoid, A is the area of cross section of the solenoid, and then the formula becomes phi equal to mu naught NIAN. Then we substitute the value of small n, that is the number of turns per unit length, and the number of turns are capital N and length is L. So that's why phi equal to mu naught capital N upon L IAN. And when you solve it, you will get mu naught, this n and this n, that is n square upon L IA. Mark this equation 1. And then we know that just we have learned phi is equal to Li. Then you substitute this value in equation number 1. Then what you will get? You will get Li equal to mu naught n square I A upon L, small l, length of the solenoid. Then this I and this I get cancelled. So what you will get? You will get L equal to mu naught n square capital A upon small l. So this is the formula which we are getting for the coefficient of self-inductance of a solenoid. Here the medium inside the solenoid is air. So that's why it is called air-cooled solenoid. If the medium inside the solenoid we change, then what happens? If we say that a solenoid is filled with magnetic material of relative magnetic permeability mu r, then what happens? Then this expression becomes L equal to mu n square A upon L, and the mu is mu r mu naught n square A upon L. So in that condition, the expression becomes L equal to mu r mu naught n square A upon L. So from here, it is very clear that coefficient of self-inductance of long solenoid that depends on to the nature of medium and square of number of turns, area of cross section of solenoid, and of course length of the solenoid. So in other words, we can say that self-inductance of a coil depends on its geometry and on the permeability of the medium. Now, what is back EMF? Another topic that we have to take. Back EMF is self-induced EMF. That is called back EMF, as it opposes any change in the current in a circuit. As you understand, by the self-inductance definition, it is the property of the coil by virtue of which it opposes any change in the strength of the current, whether it is a growth or decay, by inducing an EMF. And that induced EMF is known as back EMF, opposes any change in the current in the circuit, whether the current growth or decay, increases or decreases. Physically, the self-inductance plays the role of inertia. It is the electromagnetic analog of mass in mechanics. Means it plays the same role as mass plays in mechanics, and the self-inductance plays the same role in electricity. So we have to find out magnetic potential energy in an inductor. As you learn, as we close the key, then the current starts increasing through the coil, but it takes some time so that it achieve to the equilibrium condition or establish a current so that a device can flow up or works. So same way here, the work which is done for establishing a current in a circuit, that is known as magnetic potential energy in an inductor. So the work needs to be done against the back EMF for establishing the current in an electrical circuit in which the inductor is connected. This work done is stored as magnetic potential energy. So what is that work done? And that work done we have to calculate with respect to the time. So that's why we say that rate of work done is dW upon dt, which is equal to EI. Rate of work done is basically the power, and the power in the electrical circuit is the product of current and voltage. So that's why dW upon dt equal to EI. Mark this equation number first. And then if we say that the resistance of the inductor is very less, then we can ignore the resistances, losses, and consider only inductive effect. We are considering the ideal inductor, assuming that the inductor's resistance is 0. So that's why we ignore resistive losses and consider only inductive effect. So in that condition, we can say that E equal to L di upon dt, and substitute this value in equation number 1, then what you will get, dW upon dt equal to Li di upon dt. Now this dt and this dt get cancelled, and finally you will get dW equal to Li di. But this is the small amount of work done. Then we have to find out the total work done so that the maximum current can establish in an electrical circuit. So for that purpose, what we do? We integrate it. So when we integrate it, then the limits are 0 to W, that is dW, and then equal to L integration 0 to I naught IDI, where I naught is maximum current. So when we integrate it, then it comes W equal to L, and integration of IDI is I square by 2. Then limits are 0 and I naught. So when we open it, then upper limit minus lower limit. Half we take outside, then half L, and substitute here upper limit minus lower limit, that is I naught square minus 0 square. So finally what you get? W equal to half L I naught square equal to U. U is the representation of magnetic potential energy in an inductor. So U equal to half Li naught square is the magnetic potential energy in an inductor. Now some important points for the self-induction as what you have learned, and that I summarized here in some points. The first point is that the direction of induced EMF is opposite to the direction of EMF of the battery so that it can opposes. And now the second point, this result in a gradual increase in the current to its final equilibrium value. And third point, the induced EMF opposes growth or decay of current in the coil and hence delays the current to acquire the maximum value. Fourth point, self-induction is also called inertia of electricity as it opposes the growth or decay of current. Now we recapitulate in the form of multiple choice questions. So whatever you have learned today and that you apply your concept, solve the MCQ questions and then you check the answer whether it is correct or not. First question is here, if both the number of turns and core length of an inductor is doubled, keeping other factors constant, then its self-inductance will be. Now the options are here for you. The A is unaffected, B is doubled, C is halved, D is quadruplate. So apply the concept, what you have learned. And after applying the concept, you will get answer B, that is doubled. Apply which formula you have to apply here? L equal to mu naught n square A upon L. And you substitute the values, whatever is given in the question, and then you solve it, you will get answer B is correct. Similarly, now the next question is here, an EMF of 200 volt is induced in a circuit when current in the circuit falls from 5 ampere to 0 ampere in zero point 0.1 second, then self inductance of the circuit is. Options are here. A 3.5 Henry, option B 3.9 Henry, option C 4 Henry, option D 4.2 Henry. Now apply the concept, whatever you have learned, solve it, then you will get answer C is correct. That is 4 Henry. Similarly, the third question for you, if number of turns per unit length of the coil of a solenoid is doubled, keeping other dimensions same, then its self-inductance will be. Further, whatever you learn, apply your concept, find the answer, and your answer is here. Check it whether it is correct or not. Answer C is correct. That is 4 times. Now the next question, the energy stored in coil carrying current I is U. If current is halved, then energy stored in the coil will be. Your options are here, U by 2, U by 4, 2U and 4U. So you apply the concept, whatever you have learned, and then solve it. That is, you apply the formula U equal to half Li square, and then you can solve it and find the answer. And you see that your answer will be P, that is U by 4. Similarly, the fifth question for you, the self-inductance of a coil is directly proportional to. Options are here. The first option, its length. Then B option, resistance of the coil. C option, the number of turns. D option, the square of number of turns. So it is a simple question directly based on to the formula L equal to mu naught n square A upon L. So that's why the answer D is correct. That is directly proportional to square of number of turns. Now Question number 6. Whenever current is changed in a coil, an induced EMF is produced in the same coil. This property of the coil is due to, your options are here. A option, mutual induction. Option B, self-induction. Option C, eddy currents. Option D, hysteresis. So whatever you have learned, in the same coil, EMF induced. So that's why this is self-induction. So your answer is here. Answer B, self-induction. If you like my video, then like it, subscribe, press the bell icon. Thank you. Have a nice day.